Welcome back, students. We're going to be going over part two of this lesson. This is going to be confidence interval for a population proportion. You'll see this fancy formula down there, and we'll get into what that means in a second. So first thing we got to remember is just like any sampling distribution problem, we have to meet a few certain conditions to be able to do confidence intervals. So we want to make sure that we're sampling randomly. We want to have a unbiased estimator. We don't want to be sampling more than 10% of the population. Remember, this allows us to calculate the spread and assume independence. So those are very important. And I'm going to write those on there, and you should write those as well. And as far as our large counts goes, we want to make sure our number of successes and failures are at least 10. Notice that that says p hat and not p. And the reason is we don't actually know the population proportion. So since we don't know it, we have to use our estimate. And our estimate is going to be our sample proportion. And that sample proportion is going to be good enough in this case to meet our large counts conditions. What it's going to end up doing is it's going to give us a standard deviation that's a little bit off, probably. So we don't call it the standard deviation, but we'll talk about in our formula sheet what that looks like. As you might remember from the last video, a confidence interval is your point estimate plus or minus your margin of error. So it'll be between some number and some number. And that margin of error is dependent on a couple of things. The confidence level you set, so how confident or how unconfident you want to be, I guess, for lack of a better term, and for the sample size and the actually there's three things: the sample size, the sample proportion, and the confidence level. And those are all going to affect your margin of error a little bit. So let's figure out how to calculate that margin of error because that seems to be what we need to do to be able to do these mathematically. So first thing is when you get your big formula sheet, you're going to have a lot of formulas on there, but you're not going to have this, okay? This formula right here is not on your formula sheet, but that's the formula for the confidence interval for one proportion. So the first thing is we got to figure out what is on your formula sheet that we can use to take to our advantage. So I'm going to pull up our formula sheet for a second. First thing you might notice is on your formula sheet on the front side, you are going to have this generic confidence interval formula. Okay, it's going to look like this. And it's going to have this statistic plus or minus some critical value times the standard error of the statistic. And that's all you're given on this here. So that statistic right there, that is your point estimate. And then this critical value multiplied by the standard error is your margin of error. So that's all we have to work with on that side. If you flip over to the back side of the formula sheet, you'll see some other things on here too. So I might as well just show you now so we can get used to what they look like. You might remember that there's all these sampling distribution formulas that we learned in the previous unit. But if you go over here, you're going to have this standard error of the sample statistic. And that you might remember is on your formula for the confidence interval. So that looks familiar, doesn't it? In fact, it's the same thing as this, except for this is going to be the sample proportion. Well, we can get that because we're going to be doing samples here. So we're going to be making those estimates. So let's go back to the problem that we're looking at. So remember, on your formula sheet, this is given to you, statistic plus or minus critical value times standard error of the statistic. And this is also given to you on the back side, p hat 1 minus p hat over n, all under the square root. What we're not provided is the critical value here. How do we get that? Well, that really depends on the confidence level, and that's why we don't have it in this case. So let's talk about what that looks like and how to get it. Okay, the critical value, it seems complicated. It's really not. It's based on the normal curve, and it has specifically to do with your confidence level. Your confidence level is what sets the critical value. So if I'm given a 95% confidence level, that critical value is going to be a larger number than if it were 90%. But if I wanted to be even a larger critical value, it would have to have a higher percent. So it's based on your confidence level. So the level is going to be set at the beginning of the problem, okay? Your standard error is this standard deviation formula, except that it has the sample proportion instead of the population proportion, since we don't know the population proportion. So combined with those two things multiplied together, that gives you your margin of error. Now let's talk about this critical value for a second. It's based on the normal curve. You might want to memorize 1.96. It is the critical value we use for a 95% confidence interval. But where does that come from? Well, let's talk about a normal curve for a minute. Remember how if you go out two standard deviations from the middle, you get about 95% of your data. Well, it's not really two, it's close to two. It's actually 1.96. We round it to two just to make things easier for earlier calculations. But that two standard deviations plus two and minus two is going to give you about 95% of your data. So it's actually 1.96. And if you think about it in z-scores, positive 1.96 would be 1.96 standard deviations above the mean, and negative 1.96 would be 1.96 standard deviations below. Well, how do we get that? We don't want to sit there and try to estimate those for all those. We use the normal curve. Specifically, we're going to use the inverse norm. So let me show you on Newton calculators first how to get that, because it's actually easier. So if you have one of these TI-84 color editions, pull it up, go to second vars, go to inverse norm, and make your area whatever confidence level you want. So if I want a 95% confidence level, then I'm going to do 0.95. But we're going to do center. We want to do the middle 95% of the data. We go down and go to paste. And notice that there's a negative 1.96 and a positive 1.96. Critical values are just positive numbers because in your formula, it's plus or minus anyway. So 1.96 would be your answer. Now, most calculators, not all calculators have the center option. So if you look at the older models, let me show you an older model here that you might see something like this. And notice that you don't have the left, center, and right. In this model, you only have left as an option. So what you're going to do is you're going to average that 95% with 1. So add 1 plus 0.095 or 0.95 and divide that by 2. Keep your mean and standard deviation at 0 and 1. Remember, these are z-scores. And you'll get 1.96 this way. You can also do it by going to inverse norm and doing 1 minus 0.95 divided by 2. Well, that gets you the negative z-score, but it's still 1.96 because these are perfectly symmetric. So you have a couple different ways to do it. By default, I'm going to usually refer to this method because this works for all calculators, and you'll get your 1.96 this way, how you do it. So some confidence, some popular ones, obviously for a 95% confidence level, it is going to be 1.96 for 95%. These other ones, you're not required to memorize these, but let's go through and calculate those from our calculator. And I'm going to use the one that works for all the TI-84 calculators. So I'll do 1 plus 0.9 divided by 2, keep it at 0 and 1. In my inverse norm, you get 1.64. We'll do the other 3. And just a few quick calculations in there, you'll get these confidence levels. Now, you don't have to memorize these numbers. You just have to memorize the process. The question says, what happens to the critical value as the confidence increases? Well, it gets bigger. And how would this affect the width of the interval? It's going to get wider. And that's just due to the fact that you're multiplying by that critical value. So if you multiply by a bigger number, it's going to have a larger margin of error and be wider. So now we can put it all together. We're going to look at a problem where we're checking the conditions, calculating the point estimate, getting the critical value, calculating the standard error, margin of error, and constructing the entire interval. So here's the scenario. In the activity where you had to estimate the proportion of blue beads in the jar, suppose that the jar contained 3,000 beads. You wish to construct a 97% confidence interval for P. Let's say that the class had a combined random sample of 270 beads, with 80 of them being blue. Part A, verify the conditions for constructing a confidence interval for P are met, random 10% and large counts. B, what is the point estimate, P hat? C, what's the critical value, Z star? D, calculate the standard error of P hat. E, calculate the margin of error. And F, construct a 97% confidence interval for the portion of all beads in the jar that are blue. Write the interval in both ways. Start with the first part. So remember for the conditions, we want to check the random, 10%, and large counts. So for our random, look at the problem. It states that there's a random sample of 270 beads, so I just copied that down. Let's now check the 10% condition. Our jar contains 3,000 beads. If you take 10% of those 3,000 beads, that's going to be 300. Our sample size is only 270. So since that's less than 300, we've met the 10% rule. We're not sampling more than 10% of our beads. Finally, let's check the large counts. Well, in this case, we want to make sure that our number of successes, in this case, blue beads, and the number of failures, non-blue beads, are at least 10. And if you look at your numbers here, we don't actually have to calculate them. They're right in our problem, right in front of us. The number of blue beads in this case is going to be 80. So 80 blue. So I know that my n times my sample proportion is going to be just 80. There's 80 blue beads. So the number of failures would be whatever the remaining beads are. So in this case here, it's just going to be 270 minus 80, and that's going to be 190. So if I were to look at both of those, since 80 and 190 are both greater than or equal to 10, I've met this condition as well. So my large counts are both 10 or more. My sample is less than 10% of what my population is, and I'm doing a random sample. So I can actually do the calculations, and those will always be the easiest part of this. So the point estimate is what our sample proportion of is. In this case, what's our proportion of blue beads? So I have 80 blue beads. So my sample proportion is going to be 80 blue beads out of how many am I sampling? 270. So this is my sample size. So 80 out of 270. And that's going to give you 0.296. We'll write it as a decimal because that's how we're going to write our confidence intervals anyway. Part C, what is the critical value Z star? So we're going to look at our confidence level, and our confidence level is 97%, and that's going to drive what our Z star is. So since I have for all calculators, I want to be able to use the same thing. I'm going to go into my inverse norm. I'm going to look at my confidence level, which is 97%. So I'm going to do parentheses 1 plus 0.97, and then divide that by 2. And I'm going to keep it left, and my critical value, my Z star, will be 2.170, so 2.17. You can also do your inverse norm if you have a newer calculator and just do 0.97, but make sure you click on center to get your two, and always use the positive, so 2.17. So do you have to show work for that? No, we don't show work for the critical value. So Z star is going to be 2.17. Let's talk about the standard error. Now that formula is going to be from your formula sheet. So remember, it looks like this: square root p hat 1 minus p hat over n. Looks familiar. It's basically the standard deviation formula with the sample proportion, not the population. So we're going to plug in everything we have. We have our n, which is 270. So it's just a matter of going into your calculator and putting in 0.296, parentheses 1 minus 0.296, close it up, and then divide by 270. Always show that work. So we'll go into our calculator and see what you get. And we'll put it right over here. And you will get about 0.02778. So we'll round that to maybe 4 spots. 0.0278 is fine. For the last part, we're going to calculate the margin of error. And that's just a combination of multiplying your critical value times your standard error. So critical value times your standard error. And we'll fix that. I wrote critical value times MOE, margin of error, but it's actually what we're calculating. So critical value times standard error. So since we have our critical value, 2.17, we can multiply it by our standard error. If you don't feel like rounding, you can scroll up and just press enter. We don't have to be super precise right now, since we're going out several decimal places. So our margin of error is about 0.060326. which I'm going to say about 0.066%. So I have my margin of error. Maybe go out 4 spots, 0.0603. So now that we have our margin of error and our point estimate, we can write our interval. So remember our point estimate was 0.296 and our margin of error was 0.0603. We can put those two together and write our formula. Finally, part F, construct a 97% confidence interval for the proportion of all beads in the jar that are blue. Write the interval in both ways. We've done all the work, we just have to put it together. Remember, a confidence interval is our point estimate plus or minus your margin of error. And using our 0.296 and 0.06, we can simply write 0.296 plus or minus 0.06. That's not a very practical way to write our confidence interval, so that's why I say write it in both ways. The other way is to actually do the calculations. So if you do 0.296 minus zero point 0.6 or 0.06 and 0.296 plus zero point 0.06, you can get your low and high end. So let me see if I can do that in my head. That's going to be 0.236 comma 0.356. So your confidence interval can be written as almost looks like a coordinate. So the low end is going to be about 23.6% and the high end will be about 35.6%. Now these are estimates. We rounded. We didn't have a specific calculator function that gave us those numbers. There is going to be one, which you'll see in the next lesson. But for right now, we just got to get used to using these formulas. So one more check your understanding. You might want to pause the video and try this one on your own based on how we did the previous problem. So let's read through it, take a minute to pause it, try it, and then you can unpause it and see how I go over it. According to a 2022 Pew Research Center report, 75% of U.S. adults have read a book in the previous 12 months. This estimate was based on a random sample of 1,502 U.S. adults. Part A, verify the conditions for constructing the confidence interval are met. B, what's the point estimate? C, what's the critical value for a 99% confidence interval? D, calculate the standard error. E, calculate the margin of error. And F, construct a 99% confidence interval for the proportion of all U.S. adults who've read a book in the previous 12 months, right? And in both ways. All right, here we go. 3, 2, 1. For the random condition, we have a random sample of 1,502 U.S. adults given to us in the problem. We are going to assume that that's less than 10% of all U.S. adults, so we should be fine calculating the spread. In our large counts, we're not given the number of successes and failures. We're given the actual sample proportion, so you'll actually need to calculate those. So 1,502 times 0.75 will get you 126.5, and 1,502 times 0.25 will get you 375.5. Those are both greater than or equal to 10, so we can do a normal curve. All right, the point estimate is actually in the problem, no calculations required. It's going to be 75%. That's going to be your sample proportion. So the point estimate in this case will always be your sample proportion. Since it's given to us, we just got to write it down. C, determine the critical value for a 99% confidence interval. So see if you can get that. I'll use it using the left one. If you use the center, that's fine. Just be consistent. So 2.5758, 2.576. Calculate the standard error of p hat using our standard error formula, which is provided to you. Notice that the formula has a S, not the sigma, because it's a sample. So just make sure you don't write the wrong notation. When in doubt, leave it out. So 0.75, 0.25 over 1,502 under the square root will give you about 0.0111. And then finally, we can put it all together. So that's actually probably a 2 there, 0.0112. So calculate the margin of error. It's a combination of your critical value and your standard error. That'll be 2.576 times that 0.0112 we calculated prior to, and you'll get about 0.0288 or 0.0289. So we can round it to maybe 2.9% if you want. And finally, we want to write our confidence interval in both ways, point estimate plus or minus margin of error, and the lower and higher limits. So we'll get those from our previous parts. Doing a couple quick calculations, we can just add them together, subtract them, and you'll get a lower bound of 72.1%, upper bound of 77.9%. So we can be about 99% confident that the the true proportion of U.S. adults who've read a book in the previous 12 months is somewhere between 72.1% and 77.9%. All right, guys, just to summarize it up, this formula, remember these two are on the formula sheet here. So the generic formula, statistic plus or minus critical value times the standard error, and the standard error formula for one proportion. These formulas down here, you'll have to know how to put them together. And as far as finding your critical value, remember if you have the newer calculator option, pick the center and you can do the area corresponding to your confidence level. If you have the old calculators for the inverse norm, do 1 plus the confidence level, divide by 2 to get the average, and then go down to pace. It always does left. Finally, your interpretations from our last video, we are blank percent confident that the interval from this to this captures the true parameter in context. And then the level, if you were to do many of these intervals, about 95% of them would capture the true parameter in context. And finally, to summarize it up, we always want to make sure we're checking out the conditions. Random sample, 10% rule, and our large count should be at least 10. That concludes it. Thanks for watching.